Alright guys, welcome to Differential Equations. This is part 2 and we're going to get a little more specific. So today we're going to solve initial value problems explicitly. So I just wanted to give an example like we did from the previous lesson. We're going to find all functions y that satisfy this equation. And we can find all of them because we're going to make a general, we're going to find a general antiderivative. We're going to find the original function and we're going to have a plus c there. So when I look at this, it's a first order differential equation. I know the antiderivative of secant squared x is tangent x, plus the antiderivative of 2x is x squared. The antiderivative of 5 is 5x plus c. So I'm not going to get into too much detail about that because you should have watched the previous video and understood how we anti-differentiate that differential equation. So just to note, this is not a unique solution since we don't know c. Okay, c is unknown, so to find c we would need more information, meaning we would need what's called an initial condition. So what is an initial condition? Well, to get c, we are given an initial condition. You're given a point. You're given an x and a y. Normally it's an ordered pair x and y, but depending on your variables, it might be x and t, or t and y, something like that, but it's going to be an ordered pair x and y. Initial value. So an initial value here is a differential equation with an initial condition. So when we see that word or term initial value, we understand that it's a differential equation that has an initial condition. They're giving us a point. So when we have that point, we can now find c. We can find a specific differential or specific function. Okay. So here's an example. Find the particular equation dy dx equals e to the x minus 6x of t, whose graph passes through this specific point. So there's our initial condition. So now this becomes initial value. So we're going to start the process just like we did in the last video. We're going to really just find the antiderivative because this is first order. If we find the antiderivative, we're going to find our particular equation. So we're going to really find y equals, and we're going to integrate e to the x minus 6x squared dx. Alright, so I just rewrote the problem here, and to integrate that, we get the integral of e to the x as itself, and we're going to have minus, and the antiderivative of 6x squared is 2x cubed plus c. Now in the last video, that's where we would have stopped. Okay, would have been done. That's a general solution. But this is an initial value equation because we have the initial condition. So now here in red, we're going to substitute x equals 1 and y equals 0. Okay, so 0 equals e to the first minus 2 times 1 to the third plus c. So we're substituting into our general equation. Okay, so now we just clean this up a little bit. We have 0 equals e minus 2 plus c. So c equals 2 minus e. And you can leave that. That's going to be some decimal. So now we have the specific equation. So we get y equals e to the x minus 2x cubed plus 2 minus c, and remember that 2 minus c was the c value. So it's really similar to what we did last video. We're just moving one step further, given an initial condition and finding the actual c value here. Good morning.
Morning.
All right, so example, so find the particular solution to the equation dy dx equals 2x minus secant squared x, whose graph passes through 0, 3. Again, so let's start by anti-differentiating this first order differential equation, and I've set it up here. And I split this up because there's two terms, so I split my integral into two. And I have the integral of 2x dx minus the integral of secant squared, which is here. Y equals x squared minus tangent x plus c. Again, with the substitution, I have 3 equals y and 0 equals x. So you get negative 1 plus c equals 3, so c equals 4. And there's my substitution. So I get y equals x squared minus tangent of x plus 4. That's the equation, and our domain is restricted between negative pi over 2 and pi over 2 there. Okay, so again, solve this initial value problem explicitly. It's initial value because we have an initial condition with our differential equation. So dy dx equals 3 over 1 plus t squared plus 5 to the t, times the natural log of 5. Y equals 5, t equals 0. So I anti-differentiate right here. Remember, if we brought that 3 up front, 1 over 1 plus t squared, that's the antiderivative that's the derivative of inverse tangent. So here's my general equation. Here's my substitution in for y is 5 and t is 0. So be careful, anything to the 0 power is always 1. This just becomes 0. So we have c equals 4, and my equation becomes y equals 3 tangent tan inverse of t plus 5 to the t plus 4. So again, we're doing the same thing over and over again, and we're not getting too specific here. We're looking at our first order differential equation. We're taking its antiderivative, and then we're substituting in our initial condition and solving for c. And that's what you see on these steps here. There's the antiderivative, okay? There's the substitution and the simplification, and we solve for c, and then we plug that back into our general equation. Okay, so we're not spending as much time here getting that general equation because that's what you should have done in that first video. And lastly, this one's a little more tricky, but again, solve the initial value problem explicitly. So first order differential equation equals 7 over t minus 4 over t to the 5th minus 3. X is negative 3, t equals 1. Notice how this is dx dt. So it's not y equals here, it's x equals. So be careful there. And what I did here is I split up using my integration rules. So I brought the 7 out front, and I'm integrating 1 over t dt. I bring that 4 out front, so we have minus 4 times the integral of 1 over t to the 5th dt minus the integral of 3 dt. When you have 1 over t, that integration is natural log of the absolute value of t plus, now you have to be careful here, this is a 5th power, so you're not using the same rule here. This is not going to be natural log, this is t to the negative 4, okay, minus the antiderivative of 3 is 3t plus c, so here's our general equation. Here's our substitution, x equals negative 3, t equals 1. And I simplify and I solve for c, and I get negative 1 here. And I have y equals 7 natural log of t plus t to the negative 4 plus 3t minus 1. So if I differentiate this, I should get this right here. Okay? And I'm sorry to say I did y equals there. I made a mistake. That should be x equals, right? Because if I want dx dt. And I dropped the absolute value here because I said t has to be greater than 0. With natural log, if it's 0 or less, the natural log would not be defined if we don't translate it anyway. If we just think natural log of x, 0 and less, the natural log is not defined. So it's kind of assumed, but I put that here so I don't have to draw my vertical bars there. Okay, so that is solving initial value problems explicitly. So what that means is finding the specific function for a differential equation. So these, again, were all first order. If you guys have any questions or comments, type them below, or you can email me at nicholas.bennett@dc.gov.